Alrighty, good morning. Let's kick off. We've got a total of 55 slides to get through today over the two chapters. They're not very big chapters, so we'll just Tim's just picked up the Discord link. Be joining us shortly. All right. So basically, data link layer is chapter 6, and chapter 7 is basically switching, which is also relevant to data link layer because that's the layer switching works on. So, and chapters 4 to 7 is the combination exam. Okay, so I had noticed a couple of people had done chapters 1 to 3, the exams that is on Netacad. So that's good. Now, apologies, I'm a little vague this morning because whatever's hit me's hit me rather well. So with this, we'll look at how data link layer works in the scheme of things, the topologies, and how the framing works at this level of the OSI model. This is the second layer of the OSI model. Last week we did the physical layer, so we did the cabling and that last week. Oh, that's a good point. I didn't mention last week that under Australian regulations, you need to be a licensed cabler to connect any network cabling that you make to a live network. So what does that mean? It means you basically have to be a Sparky or somebody holding a cabling license to actually formally create network cables. It's not a hard license to get, but it is something that you need to be aware of. Quite frankly, by the time you piss-fart around with getting cable, getting all your tools out and that, you might as well just rip open a patch lead and use a preformed patch lead. But at the end of the day, when we get back into the classroom, I will demonstrate how to make them, because if you're stuck in a rock and a hard place, you've got to be able to get there. Hello, Timmy.
Hello.
So, yeah, just because I forgot to mention it, can't remember mentioning the point that under Australian law, you have to be a licensed cabler to install cables in a network. It kind of is one of the questions on the first assignment. So I was looking at that this morning and I went, I can't remember if I mentioned that or not. Bad me. All right, so getting back to today. And Tim, you've missed the introduction of data link. So this is slide number 3. So you've missed a huge amount of information.
I thought so. I'm really sorry. I promise it'll probably happen again. I'll try not to allow it.
Yeah, I'm struggling today, so
yeah, no, I read that.
How we
go. Don't push yourself. If you can't do it, I think we'll manage.
And not big chapters, so we'll do this one, take a break, and then tackle the next one. So this one's 24 slides in total. So out of that, about 18 are relevant to content. The others are,
Hebrews.
Yeah,
Yeah.
this is
Yeah.
section 1.2. This is section 1.3.
Yeah.
Yeah. So, all right. Data link layer is framing. So layer 2 frames. Remember that we talked about the protocol data units, and layer 2 are frames. Layer 3 is packets. So what do we add at this layer? Well, we basically add a layer of frame headers, so the MAC headers, when we're talking about Ethernet, which is what we're concentrating on. So source and destination, layer 2 addressing is basically what we add. Now, in the case of Ethernet, that's the MAC addresses. It is not. MAC addresses are only relevant to Ethernet. When we go look at other transport protocols, we use different addressing, like for virtual circuits and things like that. We'll look at the circuit ID for the layer 2 addressing. So there's other things to look at later on in this space. But for the majority of the course, we're talking about Ethernet, so MAC addresses. We do a level of error detection here, and that's just to detect that the frame is intact, because this is where collisions occur. So we do basically a CRC check on the frame to make sure all the frame arrived intact. So the data link layer is where we cross over from our software, our operating system, and go across into our physical realm. So we have the data link layer, which basically consists of 2 sublayers, which is the logical link control, which is basically where our drivers sit for our network card, and then the MAC sub media access control, which is where our actual network card sits and converts our frame into bits to place it onto the physical medium. And this is where our physical addressing resides. And in this MAC sublayer, we'll have all the various different media modules that we use: 802.3, 211, 215. So depending on the media we're using to transport Ethernet on, depends on which submodule we use to communicate in the MAC sublayer. So packets are exchanged via various media types, as I said, and we need to accept that frame off the network medium. We need to remove that layer 2 header, and then we need to re-encapsulate it with the new layer 2 header before forwarding it on to the next hop along the chain. And just remember, we're talking about layer 2, we're talking about putting it on cable at point A and taking it off cable at point B. Now, there may be many different A to B sections in the journey for the IP packet to take, so it's only per hop that this addressing is relevant. So the address is to the next device to pick it up to take an action against the frame. Does that make sense? I feel I'm rambling. Tim's just nodding, saying, yeah, you're definitely rambling worse than normal. Yeah, okay.
Look, I wouldn't say it's worse than normal. It's one of those subjects that's very tedious, I want to say.
Yes, it is. Until we get into the command line stuff and start building networks, it's not the most exciting stuff to read. I understand that. But I promise you, we do get into some of the practical stuff of building some basic networks. So
Yeah.
Something to look forward to. Standards, our usual suspects, ITU, ISO, IEEE, you know them by now. Moving in the correct direction, please, Mark. Thank you. Okay, so topologies, we always talk in physical and logical. Physical topologies show connections between devices and how they get basically the circuit, if you like. Whereas the logical topology identifies our addressing schemes and interfaces. Now, these connections between devices in a logical topology may be virtual. Okay, so they won't show every single physical step to get you between the two devices. It'll just say device A goes through the cloud and comes out at device B. Now, there could be hundreds of devices between A and B, but we don't need to know them because as far as the logical steps are concerned, it exits the interface on A and enters on B. So that's the difference between physical and logical topologies. WANs are, how we tie all these networks together, and we can have point-to-point links, which is the most simplest form of a WAN link. It just means it's from point A to point B. Hub and spoke, if you look at it, the old wagon wheel, you basically have a star is a central site in the middle, and it spits it out connections to all the locations around the perimeter, thus providing the spokes. Okay, mesh is where we join every single system to every other system, and it's quite labor intensive and costs a fortune. All right, but it is the most redundant network we have. So because everybody is connected to everybody else, if a single link goes down or two links go down, it tends not to affect the overall performance of the network as much as a hub and spoke would. So here we have our point-to-point topology. As you can see, one connection, two connections. Now this is called a what topology? Don't say point-to-point. Is it a physical or is it a logical?
Logical.
Yeah, it's a logical, because we're only showing our nodes. We're not showing anything in between. All right. We don't know how many physical connections make up the cloud. We're not interested. So again, from all those other times you fell asleep during my death by PowerPoints, bus topology is where Ethernet started. All right, all on the shared cable and teed off into the individual sections, and all of our timings are based on this. So how long would it take for a frame to travel along that length of cable and get picked up at the other end? Maximum length. So this is what our timing is around, and we evolved from that straight bus topology into rings. So this token ring topology came about via IBM, and then we went in when hubs and switches came about. We went to star topologies and extended star topologies from there, daisy chaining down through hubs and switches. Half duplex and full duplex communication basically signifies how many devices can talk at once. If it's half duplex, only one device can talk. Okay, so you can transmit or you can receive. Can't do both. Full duplex, you can do both at the same time. You can simultaneously receive and transmit information because you're using different wires to do it. Access control, contentioned or controlled access. Most of our stuff is contention based, and we use carrier sensing multiple access collision detection, which is left from basically the bus topologies, and wireless uses collision avoidance. So in a lot of ways, when we talk about wireless LANs, it gets closer to controlled access than contention based, but it's not as controlled. That's why it's still in contention. We'll look at these in detail later. Controlled access is basically our token ring, where you basically have, in the old, not so politically correct versions of the curriculum, we used to explain it as you're sitting around the fire passing the peace pipe. Remember the old cowboy Indian movies where, whoever had the peace pipe, it was their turn to talk. So that sort of activity occurs with a token. Whoever has the token can talk. So collision sensing, multiple access collision detection is, no, that wasn't right, was it? What's the carrier sensing? See? You're all asleep already. No, nobody picked that up. So basically, remember I said in the early chapters that we all have a base signal that we use to transmit information on. So that's what we are doing with this carrier sensing. We're detecting that base signal is there so that we can transmit on the medium. And multiple access means more than one device can talk on the wire at the same time. That's why we need collision detection services, because two or more devices can talk at the same time, causing a collision. So what happens if we detect a collision? Well, we send basically a blocking signal, and every device on that bit of shared medium then goes into a random back-off timer, which basically says you will be quiet for X amount of nanoseconds before you attempt to resend information. And the process basically works as carrier sensing. Is it just the carrier signal I'm hearing, or is there data on that signal? If there's data, I'll just wait. If there's no data, it's just the carrier, I'm clear to send, I'll start transmitting. And when a collision occurs, every device goes to the I'll just listen, and then after the hold period has expired, it goes to the listening with the intent of being able to transmit. With wireless, we can't do that collision detection because our devices could be maximum range either side of the access point, so they can't actually hear each other to detect whether they're going to collide. All right, so when we're in a wired network, we've got 100 meters of cable. It can be measured and listened to quite easily. Whereas with the wireless, we've got that 100 meters either side of the access point. So a device A on the left of the access point will not hear device B on the right-hand side of the access point if it's above its radio strength. Okay, so it can hear the access point, but not necessarily all the other devices that it's contending with for the access point's time. So in collision avoidance, what we do is we let the access point control the traffic. So when a device wants to send information, sends a signal to the access point saying, I want to send you some info, and it says, it's basically got a traffic light. It says, yes, you can send, or no, you can't. Okay, so it tells what devices can have a chat when and how often. All right, the frame. The frame is made up of a header and a tail, which wraps around the packet from layer 3. And in the frame, the header is where we basically have our source and destination information for layer 2. The data is the packet that we're transporting, and the tail is basically the CRC check and stop a frame. So frames are very organized. They have a little bit sequence saying I'm starting a frame here, and at the tail it has a little bit sequence saying on the end of the frame as well. So this is what it looks like graphically. So we have frame start, the source and destination addresses, the type of data being transported, i.e. what layer 3 protocol, so whether it's IP, OSPF, whatever it happens to be. Control is where we control the flow of services. So here we look at any quality of service. In other words, is it a voice packet that we're transporting? Does it have priority service? That's under control. The packet being transported, which is the data. Error detection, which is basically just a CRC check of the frame. And then the frame stop. Okay. Now this is where the per hop can get a little bit confusing for people. So when we originally send information from layer 3, it's going, this is the original source and this is the final destination. That is our layer 3 addressing. Source, destination, layer 3. To get there, we've got to go through router 1 and router 2. And this is where our layer 2 header comes into play. So from our original source, this is the layer 2 source, and routers 1 is the layer 2 destination. This tells it, router 1, that it has to pick up the frame and do something with the frame. It then picks up the frame and says, oh, you're trying to get to this network 172.16, and to get there, I have to send you to router 2. So I've already pulled off the layer 2 headers. So I'll put you on this interface over here, outbound, and this becomes my source MAC address, and this becomes my destination MAC address. So it has brand new headers for the next leg of the journey. Router 2 picks it up, does the same thing, looks at the destination and goes, you're on this outbound interface. This now becomes the source MAC address, and this is the destination MAC address. The layer 3 packet does not change in transit, only the headers at layer 2. So layer 2 framing tells it device to pick it off the cable. It removes the headers and the tails, looks at the packet, actions it, re-encapsulates it, and moves it along. Thus, per hop. Each media type has a different set of layer 2 framing information that it needs to apply. Remember when I said each MAC sublayer has its module, and we talked about Ethernet wireless being 802.11, then we talked about Bluetooth being 15 and that, but the other ones are, some of the other ones are point-to-point protocols, high-level data link control, frame relay. We will be looking at point-to-point and a little bit of frame relay later on, unless they've drastically changed the protocols we look at in the next series of modules. So coming to an end, data link layer, we looked at how it prepares the frame for transmission over the medium that is being used to transmit the frame. We looked at the two sub layers in the data link layer, logical link control and media access control. And we had a look at the various topologies, physical and logical, and some of the topologies to types as far as point-to-point, star, that sort of thing. We looked at how we detect errors during transit at layer 2, and we look at what the addressing type is used for and how it is used in conjunction with layer 3 addressing to get us to our final destination. And that would be chapter 6 in a nutshell. So
that was exciting.